A cylindrical shell of radius a carries a uniform charge density rho. Use Gauss's law to determine the electric field of vector E. Okay. So we got this. So first thing, draw a picture. Draw a picture. Whoop, whoop. That looks good. So we have a hollow cylindrical shell, and we have a radius of, let's say A, because they give us right here. Whoop, A. And we have a uniform charge density of rho. So I'm going to rewrite this rho as a surface charge density. That might be what the S is anyway, surface charge, but I prefer sigma. I like to use rho for volumetric density. So we have sigma here, which is a surface charge density, which is a small unit of charge, Q, for a small unit of area, A. And we have Gauss's law, which is electric flux equals double integral E dot dA equals Q enclosed over epsilon naught. And this is a closed surface area. So from here then, what we're looking at is we're trying to find the electric field E, so that part right there, for rho. I'm going to rewrite this as R. I like R as radius. Radius less than A and radius greater than A. So, okay. So it says for a given radius, so looking at this from a different angle, we're going to look at it from straight on. So we have something like this, a circle. That's surprisingly good until the end. There we go. So we have radius A here, and then we have a radius R. So what we're going to do then is we're going to find the area. So at a given R, we have something like this. And we're going to do a surface integral of a closed surface, like so. Yep. And to draw the same thing over here, we're going to go like this, but since we need a surface, we're going to go all the way back. So we're going to have a small concentric cylinder, so to speak. So then, what we have, let's see here, we're going to look for the electric field at this point. Now the electric field at this point is going to be the same at every point because it's symmetrical with regards to the shell. And so if we look at what this means here, so this E is actually a vector, that's a vector too, and this is a dot product. So this is a dot product between the electric field and dA. The way you make a area into a vector is you draw the normal. So if this is kind of, let's say it's kind of off at a funny angle here, then this would be going off this direction and then be a right angle. So the normal vector would be the way you draw the vector for dA. And so what this is then looking for is the electric field that's coming out from the area. That's along the same line as the normal vector. So right here, what the dot product means is the amount that's in the same direction. So this is probably a little bit more background than you need. That's fine. That is fine. So you have an E here, you have an A here, and then you do the dot product. It would be the projection along, so it would be the amount of E that's along A. Long story short, they're in the same direction. Another way of thinking of the magnitude of the dot product is cosine of theta, where theta is the angle between the electric field and the area. In this case, they're both the same, they're both pointing in the same direction, so this cosine theta becomes cosine of 0, which is 1. So enough background talking justification. what this really comes down to then is we can pull the electric field out of the integral, because as far as anything is concerned in life, it's a constant. And for this equation, it is considered a constant. So we have electric field times double integral surface area dA. And there is the way we got rid of that dot product is there's the cosine theta. That cosine theta is 1. We're multiplying by 1, and so now the dot product is gone. Q enclosed over epsilon naught, and then we have electric field equals, now this is just the area of this concentric cylinder we made. So the Gaussian surface is a volume, a shape that with surface area. Yeah, I guess that's not a good explanation. It can be any shape you want, but we chose the shape so that the electric field is parallel with the dA vector, with the normal vector for the area. So it's a concentric shell. So we're going to find the area of this concentric shell where the radius of this concentric shell is less than A, less than the cylindrical shell that we're given. So we have Q enclosed over epsilon naught times 1 over the area here, which would be 2 pi r, which is the it's circumference of a circle, but it's kind of the circumference of the base of the cylinder, times L, where L is the length of this cylinder. Your first thought is, well, isn't that length infinite? How can we have an infinite there? It's probably infinite. We're assuming it's infinite. And the idea is we're hoping it's going to cancel out with something else. Now we need to find out what this Q enclosed is. This Q enclosed, so we had a Q over here. We were given a surface charge density. So I'm going to say that dQ, we're just going to rearrange this equation over here, equals sigma times dA. So to find the total charge, we would then integrate both sides. Whoop, whoop. We get total Q enclosed would equal sigma, which is just a constant, times the total area of the bigger shell, which is going to be 2 pi, nope, not r, 2 pi a times length. So it'll be the same format as our Gaussian shell, which was smaller and inside, but the radius will be bigger. So we have 1 over epsilon naught times sigma, surface charge density, times 2 pi a, that's the bigger radius, times length, which we're assuming is about infinite, 2 pi r, where r is less than a, times the same infinite length. Do some canceling. Two pi, nope, go to a different color, offer better contrast, 2 pi L over L, and we're left with sigma A over R, epsilon naught. Okay, so this is the electric field for Q enclosed with a cylinder over cylinder, but I made a mistake here. So what I said was we had some Q enclosed. The problem is this cylindrical shell of radius A, the uniform charge is on the outside of our inner radius. So to look at this from a head-on point of view, we have, this is where we're doing our Gaussian surface with radius r. This is A, that's where all the charge is. So when we have this Gaussian surface on the middle, our Q enclosed is 0 because we don't enclose any Q. So we do the same thing here, but then we do Q enclosed equals 0. Now you have this second situation here. So this one for part A, clean up the board slightly, get rid of the riffraff. This one, there will be 0 Q enclosed. There'll be 0 enclosed charge because it's on the interior of the shell. Now for this one though, where R is bigger than A, we do have some Q enclosed, and that Q enclosed is going to be represented this way that we did before, that I showed you here. And so then we put in the, use the surface charge density, find the enclosed charge, do some canceling, and that's when we get this answer right here. Whoop. Make it a little bit smaller. Where we have surface charge density times the radius A of the shell divided by epsilon naught over R. And for this, A has to be less than R. And that's how we do the first part. So the key to this was we say that electric field dot dA is the same. You can get rid of the dot product because you're going to say that the two vectors are parallel. And then you're going to say that the electric field is constant so that you can pull it out of the integral. And then you're just left with two surface areas calculations. And then you use those. So let's do the second part then. Boom, boom. A spherical shell, radius A. Spherical shell, radius A carries a uniform charge density rho. Use Gauss' law to determine the electric field vector E. Spherical versus cylindrical. Okay. So same idea, except now we're doing spheres versus cylinders. But when you use a head-on view, it's going to look fairly similar. Either way. Excellent. So we have here, we're going to start with doing the inner one. So this will be R. This will be A. We'll start out the same way. The electric field will be coming outwards like a point charge. And so we have double integral E dot dA equals Q enclosed over epsilon naught. We're given a uniform charge density. I'm going to call that a surface charge density. So sigma will be my surface charge density. I'm going to say that's a small amount of charge for a small amount of area. I like to start off by saying it's small amounts because that way, if we want to use it as an integral, it's easier to kind of make that leap of faith. So we have, rearranging this, we have delta Q equals sigma delta A. Integrate both sides from 0 to infinity. We get all the Q there is. I'm going to call that Q enclosed. I should probably call that small q enclosed just to be consistent. And then that would be sigma times all the area. So rearranging this, the electric field will be constant because we're at a for a given radius. For a given radius, it'll be symmetrical about the center, and it'll be symmetrical and concentric with the outside shell. So that for any given point, the electric field will be the same. Kind of like if you go anywhere on the Earth, more or less, gravity will be the same because you're the same distance from the center. So then we have E times, we'll do dot dA. This here is just the surface of our Gaussian sphere, which is the smaller one, equals Q enclosed over epsilon naught. Now at this point for part A, I'm going to say that this Q enclosed there, that's 0. So when we have a small concentric circle inside, if we're looking for the electric field inside this shell, that our Gaussian shape is going to include 0, it's going to hold within it 0 charges. And since it has 0 charge, that's going to mean that there's no electric field. So the only way that you can make this side equation equal 0 is if electric field is 0. Therefore, electric field equals 0. Come back here. This one, 0. Okay? Now, for this one, the roles are reversed, and we say this is A, but R is something bigger. So now there will be an enclosed charge. So we'll do the same process, get down to this point, and then we have Q enclosed. So Q enclosed will be sigma times area. Area of a sphere is 4 pi r squared. Except we're not going to use r because we know the radius is a, 4 pi a squared. all over this, which is the area of our Gaussian shape. And that will be also a sphere. So 4 pi, and we can choose any Gaussian sphere. We just want to choose a Gaussian sphere so that the electric field is either parallel or perpendicular to the area at every point. So the easiest way to do that in this case is to choose the same Gaussian shape that we're trying to find the electric field. The same shape for our shell should be the same shape for a Gaussian sphere in this case. That way, all the electric field lines will be parallel to the electric field at every point. Electric field lines will be parallel to the shape. Okay, 4 pi r squared. Do some canceling. Whoop. Cancel, 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 cancel. And we're left with sigma a squared over r squared. And then this will be kind of like a point charge. You remember a point charge, you have 1 over 4 pi epsilon naught q over r squared. Q over r squared as the how the electric field drops off at distance. And if you look at this, we have some amount of charge here that's again dropping off by an r squared distance, which kind of makes sense. So when you get outside of the sphere, it's going to act as if it's a point charge. It's kind of sort of a point charge with the same amount of q enclosed as if that q enclosed, the charge enclosed, was just a point charge. So basically you could take this, once you're outside the radius of this spherical shell, you could just crumple up that spherical shell and just make it a point, and you'd have the same electric field resulting from it. And this is how we use Gauss's law on a couple common shapes, a cylindrical shell and a spherical shell.